Okay, so today I'm going to do what I hope is a quick introduction to capacitors in chapter 24. This is a chapter that I sometimes skip and go right on to electrical circuits in chapter 25 because there's some stuff in chapter 24 where it actually talks about capacitors and electrical circuits, and we haven't talked about electrical circuits yet, so I find the order a little bit perplexing. It does follow up nicely on what we talked about in chapter 23 because a capacitor you can really think of as an object that stores electrical potential energy in a circuit. So in that way it makes kind of sense. But I think most people think of a capacitor as an element in an electrical circuit. So in that sense it doesn't make any sense to talk about it before you talk about electrical circuits. So I'm going to do a really quick intro to capacitors today just so we're familiar with the vocabulary. I don't think I'm going to assign any chapter 24 homework at all. We're just going to do this quick intro, then go right into chapter 25 with resistance and simple electrical circuits. So what is a capacitor? The simplest way to think of a capacitor is just as the way it's usually drawn in an electrical circuit is just two parallel plates of metal, each of which holds an electrical charge. Usually you imagine one plate holds a charge of plus Q and the other charges minus Q. So there's an electric field between those two plates. The electric field lines are going to point from positive to negative, and that electric field will be constant and uniform in that gap. But electrical charges can't flow through that gap because they're separated by a gap of either air or some kind of non-conducting material. If you put non-conducting material between the plates of a capacitor, we usually refer to that material as a dielectric. And your book chapters may go into a little more explanation of what that word means. For our purposes, just think of a capacitor as two conducting surfaces separated by either empty space or air or some kind of non-conducting medium. Capacitors don't have to be shaped like two parallel plates. Actually, we'll see later on in the chapter you can have cylindrical conductors, you can have spherical conductors making a capacitor. You can also take these two parallel plates and roll them up into some other shape. In fact, in actual electrical circuits, oftentimes when you see a capacitor in the real world, what it looks like is just a little cylindrical object on a circuit board with two wires coming out of it. And those capacitors are typically two thin bits of metal foil with a non-conducting material in between them that are then rolled up into a compact cylinder, so they take up less space than two actual honest-to-goodness metal plates would take up in a circuit. So what does a capacitor do? A capacitor you can think of as just storing electrical charge. Electrical charge piles up on one side of the capacitor, positive, the other side, negative. And a capacitor in a circuit generally charges up to some maximum charge, and then electrical current stops flowing because electrical current can't flow across that gap. And this will all make, I think, a little bit more sense when we talk about electrical circuits, because we haven't really talked about what happens in an electrical circuit. But as far as capacitors go, you can imagine you've got these two parallel plates. You have a battery that has a positive terminal and a negative terminal, and you connect the positive terminal to one side of the battery and then to the capacitor, and the negative terminal of the battery to the other side of the capacitor. And what you get then is you get an electrical circuit, but that electrical circuit is broken because electrical charge can't actually flow through the capacitor. What happens though, and again we haven't talked about circuits, so this is a little bit of a preview, is the positive side of the battery pushes electrons away. Sorry, that's wrong. We have to be careful with the conventions that we use for charge in physics, because the convention we use for electrical current is backwards from the convention we use for charge. But current will actually flow through this capacitor until the plates of this capacitor are filled with a certain amount of electrical charge. We'll see what that amount is in a minute. So if we imagine the electrons in a wire, the electrons in this wire will be attracted to the positive terminal of the battery and repelled from the negative terminal of the battery, which means that negative charges will accumulate on this side of the capacitor and positive charges will accumulate on this side of the capacitor. And that will happen until if you imagine positive charges here on the capacitor and a positive terminal of the battery, until the amount that the capacitor is pushing charges this way is equal to the amount that the battery is pushing charges this way, and then the charge will stop flowing. It'll stabilize when this capacitor is fully charged with a charge of plus Q on one side and minus Q on the other side. Okay, so a capacitor stores up a certain amount of charge when you connect it to an external source of what we call potential difference or voltage. How much charge does a capacitor hold? Well, we define a property of a capacitor called its capacitance in terms of how much charge it holds at a particular electrical potential difference. So if you apply a voltage V across a capacitor, it will hold a certain amount of charge Q, and the amount of charge stored per unit electrical potential is called the capacitance. For some reason my pen, you guys probably can't see this, but the pen that I'm writing with is about a half a second behind what I'm writing, so it's like writing in slow motion. Capacitance is measured in units of coulombs per volt, right? Charge per unit volt. And I realize it's confusing that capacitance, we use the symbol C, and we also use a C, a capital C, for the unit of electrical charge, which is a coulomb. It's one of those things. There's only so many letters, so we've got to deal with it. And a coulomb per volt, we actually give its own name. It's called a farad, named after Faraday. So the unit of capacitance, the coulomb per volt, is called the farad. Okay? Most actual physical capacitors that you will encounter in the real world hold very, very tiny amounts of charge, and so the capacitance is a very, very tiny number. Typically, real world capacitors have capacitances of microfarads, nanofarads. You'll even see pico farads. It's 10 to the negative, what's that, 12th, 15th, 12th, 10 to the negative 12th, trillionth of a farad. So a farad is a huge capacitance. And a capacitance is just a property of a capacitor that is essentially determined by its geometry. What your book next does is it calculates the capacitance of a parallel plate capacitor based on what we know about the electric field in the region between those two plates. We, back in chapter 21, found the electric field due to an infinite plane. We found it in chapter 21, just directly integrating the electric field. We found it again in chapter 22 using Gauss's law. And what we found is that the electric field near a conducting surface that we can regard as essentially, effectively an infinite plane is equal to the charge per unit area divided by epsilon naught. I guess I should highlight this. The answer we got, the electric field is equal to the charge per unit area divided by epsilon naught. If we're talking about a capacitor with a surface area that's got a constant charge per unit area on it, that sigma we can just write as Q over A. So the expression for the electric field is Q over epsilon naught times the area. The electric field in that gap between the plates of a parallel capacitor then in here will be equal to just this Q over epsilon naught times the area of the plates, and it will be constant. Remember, one of the interesting results of this chapter 21 problem was that if you're near an infinite plane of charge, the electric field actually doesn't depend on distance. It is constant and depends only on the charge density. And so the electric field lines are parallel to one another. They don't diverge. And the electric field is constant with respect to distance. So if we build an actual parallel plate capacitor and we are in the middle of that capacitor, nowhere near the ends, then in here, in this region of space in the capacitor, the electric field lines are essentially parallel and the electric field is constant with respect to distance. If we want to know the electric potential in this gap between the plates of a capacitor, this relationship between potential and field is that the potential difference between 2 points in space is equal to the integral of the electric field from point to point, the integral of E dot dl. If we imagine starting at a point A and moving to a point B in between the two plates here, just moving from one plate to another, then the potential difference between plate A and plate B is just equal to the integral of E dot dl from A to B. E is just constant, and it's parallel to the plate, so if we integrate just in a line from one plate to another, this just becomes E times the length, and so we get an expression that says the potential difference, let me get my highlighter and change color here, the potential difference between two, well that's not good, you can't see the letters through that highlighter, it's too dark. The potential difference between the two plates of a parallel plate capacitor is equal to just this times the distance. So QD over A times epsilon naught, the permittivity of free space. So the potential changes linearly with distance as you go from one plate to another. If we think about this in terms of equipotentials, right, let's do this. Let's get rid of this little drawing here and make our own drawing. If we ask what do the equipotential surfaces look like in a parallel plate capacitor, let's see. I can probably, my mouse is going crazy because I'm holding my pen in my hand while trying to use the mouse and I'm too close to the drawing tablet. Let me go to insert here and just make a parallel plate capacitor and make another one. And we want to ask ourselves, if we are thinking about the electric field in this gap in space, what does the electric field look like? We already said that the electric field is just lines that go from the positive side of the capacitor to the negative side of the capacitor. And that means that the equipotentials, and it's hard for me to draw an exact parallel line here, the equipotentials that correspond to that field will just be vertical lines. Might be easier for me to do with the mouse. Vertical lines that are evenly spaced. Okay, the equipotential surfaces from here to here. The direction that a positive charge would move in this field is from the positive side to the negative side, and the potential would change constantly with distance. Okay, the potential is just a function here of the distance. If we look back at the previous page where we had a expression for the capacitance as the charge stored in the plate divided by the potential difference. Since the potential difference is just QD over epsilon naught A, we can write that the capacitance of a parallel plate capacitor is equal to epsilon naught A over D. That's just combining this expression here with this expression here, plugging this in for V. What this tells us is that the capacitance of a parallel plate capacitor depends only on its geometry. It depends on its surface area, and it depends on the physical separation of those two plates, D. Does it make sense? The dependence on A and D, if you think of capacitance as the capacity that this thing has to hold charge, it does make sense. It makes sense that it's proportional to the area, right? The bigger those plates are, the more electrical charge they hold. And it also makes sense that it's inversely proportional to the distance. If you think about the charge on these two plates, as you push them together, those positive and negative charges are going to push apart on one another harder. They don't want to be on that capacitor. So the closer together they are, the smaller D is. Actually, no, that's backwards. Let's step back one more and think about this. You've got a parallel plate capacitor with a charge plus Q on one side, minus Q on the other side. Let me see if I can draw this over here. Okay, let me switch back to the narrow pen. Okay, so we've got plus Q here, minus Q at the edge of my thing here, minus, why can't I draw any further than that? Oh, because I'm at the, this is the edge of the active window for, I'm not stopping and taking another take of this. I just need to stay, I need to stay away from that edge of the screen. Let's try one more time. So here's my parallel plate capacitor, one plate, two plates. Here's my charge plus Q, here's my charge minus Q. Okay. If these plates are close together, okay, if D is small, there's going to be a greater attractive force between the positive charges on one side and the negative charges on the other side, and that will draw more charge to fill up the plus side of the plate and to fill up the minus side of the plate. So it actually increases the capacity of the capacitor to have D be small, C is bigger. So the two are inversely proportional to one another. So what we see from this, and the important thing to get from this is, I don't really care if you memorize this equation for the capacitance of a parallel plate capacitor or not. But the important thing is that the capacitance of a capacitor depends only on its geometry. It depends only on the physical shape of the capacitor, and it depends on the dielectric constant, this epsilon zero, the permittivity of free space. So far we've only talked about electric fields and free space, but this permittivity, I might be spelling that wrong, epsilon zero, if this wasn't a vacuum, if there was some material, some dielectric material in between that, then the capacitance, the capacitance would be equal to epsilon A over D, where that epsilon is the electric permittivity of that physical substance. And again, we haven't talked about electric fields and matter so far, and we probably won't talk about electric fields and matter. That's a topic that usually you tackle in your junior level electromagnetism classes. But for us, it's important to highlight the fact that the capacitance of a system is just determined by the geometry of the system. And because there are other capacitors other than parallel plates, we can actually talk about calculating the capacitance of other types of shapes. I'm not going to go over this right now. You can go over these two examples yourself They build on the electric field examples and the potential examples we did for these exact same shapes. Example 24-2 is for a cylindrical capacitor. In other words, a capacitor consisting of one long cylinder inside of another long cylinder, the inner cylinder charged with a charge plus Q, the outer cylinder charged with a charge minus Q. What is the capacitance, or rather, what is the relationship between the charge and the voltage for that geometric arrangement of conductors? Example 24-2 goes over that. And then example 24-3 does the same thing for a spherical capacitor. Imagine you've got a conducting sphere of charge plus Q inside of a conducting sphere of charge minus Q. What is the capacitance, or the ratio of the total charge to the electrical potential difference? Remember, C is equal to Q over V. Okay, what is the relationship between the charge stored on this spherical capacitor and the potential difference? By the way, a spherical capacitor would be very hard to build, because how do you get charge in an electrical circuit? How would you get charge in the inside sphere if it's inside another sphere? You'd have to cut a hole in it. So these aren't really practical examples. These are just spheres floating in space with electrical charge on them. So you can go through this example as well and see if you can set that integral up for the potential difference between the inner and outer surfaces. And the integrals are fairly easy to do. And like I said, they build directly off of the examples we did in chapter 22 and 23 for the electrical potential of these various shapes. So I don't really feel the need to go over that in detail. Likewise, we are not going to go over section 24-3. This is the reason I said that I usually skip this chapter entirely, is because this section talks about putting capacitors in electrical circuits, and we haven't really talked about how electrical circuits work yet. So it doesn't make any sense to me to do that now. We'll come back and we'll look at capacitors in series and parallel, the topic of 24-3, after we talk about circuits and series and parallel circuits in general. So we'll come back and we'll look at this relationship. One last thing that I want to look at is this section 24-4. And the only reason I want to look at this section is because the expression we get from it is actually really, really interesting. Again, I said you can think of a capacitor as storing electrical energy that you've got. It's so hard to draw a straight line with the mouse in this thing. You've got, okay, a parallel plate capacitor with charge plus Q on one side and minus Q on the other side. If you want to just think about it in terms of force, the charges on these oppositely charged plates will want to attract one another. So you can imagine there being a potential energy in space due to that electrical attraction. If you want to think of it in terms of a circuit, if you connect these two plates with a wire, okay, this generates a potential difference between these 2 points in the circuit, and that's going to want to cause electricity to flow through that circuit. You can also think about it in terms of, if you've got these parallel plates with an electric field in between them, and I put an electrical charge, say a positive electrical charge, here in space between those two plates, it's going to be repelled by the positive charges here and attracted to the negative charges here. And there's going to be a potential energy associated with the fact that that charge here is in this electric field between these two plates. So we can ask ourselves, what is the potential energy, the total potential energy stored on these plates due to the separation of these charges? And chapter 24-4, section 24-4, they actually go through this calculation. If we remind ourselves of the relationship between electrical potential and electrical potential energy and work and the field. Remember that we define electrical potential as the potential energy per unit charge. And if we want to think of potential energy of a charge, it is equal to the charge times the potential. If we ask ourselves, in order to fill up one of these plates with charge, how much total work does that take? Then every little bit of charge we add to this plate increases the potential energy. So the total work done, or the change in potential energy, is going to be equal to the integral of V dq. Every little bit of charge we add to the plate at some potential increases the potential energy. So this expression here, the work needed to fill those plates with charge, is equal to the integral of V dq from charge of 0 up to the total charge found on those plates. And then we substitute for V the expression that relates capacitance to charge and voltage. So V is equal to Q over C. And so we've got the integral of V dq becomes the integral of Q over C dq. And the integral of Q dq is just 1/2 Q squared. So this whole integral looks like 1/2. I'm going to write it like this instead. 1/2 1 over C Q squared. Okay. The potential energy stored in a capacitor is 1/2 times 1 over the capacitance, which is just a constant, times Q squared, the square of the charge on stored on that capacitor, stored on each side of the capacitor. This expression is interesting because it looks a lot like an expression for potential energy that we saw when we were studying mechanics, which is the potential energy of a mass on a spring. Okay? If we remind ourselves, thinking way back to Hooke's law, if we've got a mass on a spring, and that spring exerts a force equal to minus kx, that the potential energy of that spring when it's stretched an amount x was equal to 1/2 times a constant times x squared, where x is the position of that spring from equilibrium. And this expression for kinetic energy, that potential energy of a capacitor, equal to 1/2 times a constant, 1 over the capacitance, times the charge squared, is an interesting analogy that we will come back to later on in the course, because it turns out that the mechanical system of a mass on a spring oscillating up and down can be related to certain electrical systems that have capacitors and resistors and inductors and all these electrical elements that we haven't talked about yet. And that the oscillatory motion of a mass on a spring can be related to the oscillatory flow of current in certain kinds of alternating current systems. So the only reason I stop here and bring up this one section in particular on the electrical potential energy stored in a capacitor is because this expression will serve as a powerful analogy when we eventually talk about alternating current and when we talk about the analogy between mechanical oscillating systems and electrical oscillating systems. Okay, so that's what we're at, right at 30 minutes right there. I'm going to go ahead and stop there. No homework on chapter 24. Go over these two examples. The example of the cylindrical capacitor. Make sure you can go through the reasoning and the integral and get this expression for the capacitance. The spherical capacitor, and make sure you can go through the reasoning and the integral and get that expression for the capacitance. But we're going to leave capacitors behind for now. We'll come back to them later when we talk about more complicated circuits and series versus parallel circuits, and we'll come back again when we talk about alternating current at the very, very end of the course.